time being at 8 in the morning. This is a lot better.
Oh yeah.
And then there's a food court outside, and God, what else more could we ask for?
Yeah. So is anybody here that is not registered yet? Use one? Okay. Are you guys signing up for it? You did, right? Like you said, you are.
I'm going to.
Okay, you know. Okay. And you're?
I just got the equivalence today. So.
You got it?
Yeah.
Okay, good. And you guys?
Not yet.
Not yet, but you are waiting it?
Yeah.
Okay. Alright. So, okay, so today we're gonna focus on a couple of examples for machine learning. I hope that my TA is coming in as well, so I can introduce you to him. So we're basically just going to look at a few examples. And I would like you guys also to, for the homework, I collected like 3 interesting news articles, and one is with a video where Andrew Angie is discussing like what data scientists should know about deep learning, and I think it's an interesting lecture, and it should be like at a good introductory level, and there's a lot to be learned from this, and then there's the one article mostly about like the history of like who has been players in AI, and like how AI can really help us shape the future, and like where it can be used. So there's a lot of like basically just some reading for homework for until Wednesday next week. So it's like the homework will be due on Wednesday. I'll post it this afternoon. But mostly what I would like you to do over this week is just go out there and try to find things that are interesting, maybe for the class as resources. So for example, toolboxes to do machine learning, data sets that you think will be interesting to analyze. Maybe we can actually bring that data set into a homework. Or you can use that data set for your course project. And then other resources like challenges. There are machine learning challenges out there that could be interesting for us to maybe participate, or take a look at, like see what are the difficulties, like, and try to find ways together as a class to solve those. So it's really like an effort for you to like try to understand what the world of machine learning looks like right now, and collect some resources, and like maybe write 1 or 2 pages about this with some links and some pictures and some questions and discussion points. And I would like to spend about an hour next Wednesday to discuss what you have found and what you think is interesting. And if you have questions, you can ask that question to me or to your fellow students, and we can try to come up with an answer to those questions. The following Wednesday after that, Lixing, the TA, will give you a introduction to scikit-learn, which is a Python library for machine learning. He'll walk you through some tutorials there. During the semester, we'll also introduce some methods to visualize data with Python, and in particular, for example, if you have very high-dimensional sparse data, that's very difficult to visualize that kind of data. And there are some new methods that help you visualize these this information, like high dimensional information, on just 2 dimensions without losing a lot of the structure in your data. So we're going to work on some visualization there. We're going to do a brief introduction on 2 machine learning, like 2 deep learning toolboxes. One is Keras, which is kind of like a high-level machine learning toolbox that sits on top of TensorFlow and Theano. And then we're going to do a tutorial on TensorFlow as well later in the semester. So you'll get like a couple of tool sets introduced by Lisheng, and we might have some homeworks associated with those toolboxes and tool sets. So the Wednesdays I'll try to keep as interactive and as practical as possible, so that we have a group discussion going on, and that we have more or less like an interactive Wednesday. Some of those Wednesdays I will give lectures mostly about related topics like statistical evaluation of your machine learning experiments, or how to set up a machine learning experiment. Again, more practical, more like yeah, more of a like a handcraft, or some yeah, like a skill set that is more practical rather than theoretical. Okay, and so the Mondays we'll mostly do some lectures. Since we didn't have any time to prepare a discussion for this Wednesday, I brought a number of examples of machine learning experiments and machine learning capabilities today that I have been working on, and which are less impressive, but I also would like to start off with some very impressive recent works that give you a kind of like an idea of what's going on right now. And before we get started, I would like to just ask you like a few questions, or this question, so do you already kind of have an idea of like what machine learning could help with? I mean, you guys chose this course, like why did you choose this course? Do you just want to choose it because you heard that it's fancy now, or like there are jobs out there for this? Or is there some intrinsic interest there that you're interested in, why you want to do this? I'd like to start with you.
Well, there's a lane detection.
Lane detection,
Yes.
Okay, so for self-driving cars.
For self-driving cars.
Yeah, very interesting.
Mm.
And I think being born very close to Germany, and my university was very is set up next to Mercedes or Daimler's research center in the south of Germany, and it was very interesting to see the transition that those guys there made from a more engineering-driven approach, like LiDARs and radars and whatever, tried to avoid any obstacle that you run into, towards more machine learning and just optical-based methods. And I think it's very interesting to see that Tesla is actually right now only relying on cameras, I think. I think they also had a casualty because of that they only relied on visual cues, but I think that is a very good point, yeah. Anything else?
Drug development?
The what?
Drug development?
Drug development, yes, very interesting. I'm not an expert in that. I've heard that, I think, yeah, so I think the folding of molecules is very computationally intensive, and I was very intrigued by this work where they used crowdsourcing to solve this problem as well, where people played a computer game, so to say, and solved that problem. But yeah, that's a very, very good and very interesting problem.
Sports analytics?
Sports analytics, yeah. I think Stanford is very big in this area where, like, they use computer graphics and body computing devices to improve sports, and yeah, I think that has come a long way, and we are at ICT. We are interested in. Hey, oh, so Liching is here. Good. So everybody is Liching. So he's a PhD student of mine, and he's also the TA of this course. And so he's hopefully going to be able to help you out. I think you're going to let them know when your office hours are.
Yeah, I'll update.
Yeah, and it's going to be on Blackboard, an announcement there, so he can help you out with this. I mentioned that Wednesday after next one, we're going to introduce Scikit-learn a little bit. Okay, great. Yeah, so at ICT, we are interested in, as I mentioned, human communication. So I'm trying to understand how we humans communicate. So that's kind of like a multimodal problem. I think the lane detection or like the drug developments are more of a single modality kind of problem. On the one hand, you have like a visual problem, and on the other hand, you have like a physical, chemical kind of problem. But I think sports analytics could be multimodal, where you have either just cameras looking at the athlete and trying to improve the performance there, or you have additional performance metrics like physiological sensors. So one of the issues there that we deal with is synchronization and trying to understand how the multiple modalities work together. So that's a more complex issue, and I think we're going to have one Monday dedicated to multimodal machine learning. So that's going to be, it's more of a niche kind of area where we try to tackle very much harder problems than I think most of the machine learning community are with just like recognizing objects on a picture. We're dealing with sequences and sequences of different dynamics with different frequencies and so on. And we also try to solve other medical problems where we try to understand how human communication reflects on your well-being, and I'm going to bring a couple of examples of like what we're doing there today. And we're going to talk about some supervised machine learning experiments, some unsupervised machine learning experiments, and at the end I also show a little bit of like a regression experiment that we did in this context of understanding human behavior. So that's kind of mostly what today's class is going to be about. Just to give you a like an overview of like what is fancy and new out there right now. I mean, this is almost even like old already, and you might have realized that this field is very, very fast moving, and a lot of new companies are opening up, and even companies are, or new methods are developed around like these conferences, like for example NIPS and ICLR and ICML, that even trick researchers. I think there was a Rocket AI in December 2016, which was set up by some journalists as a fake company, and researchers went there, and like the party was cancelled by the police, and I think they got fined for that. So it's like there was a lot of interesting fake news about AI as well as politics and stuff like that going on. So it's like it's a very, very fast moving topic, and but I think it's super interesting to just no worries to investigate. So so you might have heard of convolutional neural networks, just as an example of what's happening right now. So these neural networks are really good at identifying and understanding what is present in a picture. So for example, they're used for these CIFAR data sets. I think these are some examples of the CIFAR 10 data set. They have like 10 different categories. Just airplane, automobile, deer, dog. So you can imagine it might be easy to actually distinguish between a deer and an airplane, right? It's not that hard. The visual representation is very difficult. But then there are some that might be a bit more like difficult, where cat and dog, or cat, deer and dog, or horse are pretty similar. So these networks have to understand something about the image and try to like capture what is present, what features are present in the image that like give a good idea about the category. And if you look at the different images, they can be very, very different from each other. And I mean, it could be, I don't actually know, but it could be, for example, a statue here of like Tommy the Traveler. No, what's his?
Tommy Jordan.
No, but Traveler, yeah,
Or
Traveler
Traveler,
is
or
not Tommy.
Yeah.
But Traveler is the
Tommy-
horse.
Tommy was-
So it could be, for example, even a horse as well. And so it needs something to understand shape, texture, and the pixel value. So a good way to do this is actually, if you imagine that this is the input layer, so this is the entire image with all the pixels here. So a good way to investigate what is present in the image is to look at the entire image, right? But that can actually lead to some issues where if you have an entire network or an entire layer like representing just one pixel, or every pixel goes into a hidden layer, and like these connections need to be learned, you have so many parameters that you need to tune that your data set needs to be very, very, very large to understand what's going on. And so what convolutional neural networks are doing is they kind of reduce the number of parameters that you have to learn and apply the same function. So this function of like reducing this kind of like receptive field, so like you have some knowledge about like a local area of the picture, and this function that is applied here and reduces this receptive field to like another pixel in like a hidden layer, that is applied to all of the locations in the picture. So you kind of convolve the picture, so you move this function over the entire image. And the cool thing about this is also you can parallelize that, because all of these convolutional operations can happen at the same time in a GPU, for example. So that's why these networks are super efficient, so they need to learn only a few parameters in all of these convolutions, while they would have to learn many, many more parameters in these fully connected output layers. So what people are doing right now is they train these convolutional neural networks and learn these convolutions on very large data sets and try to understand like what's happening in the picture. And some of these operations that are happening in these hidden layers you can see up there, which look like, so these are typically very similar to Gabor filters with different frequencies. So a Gabor filter is basically like a sine wave with different amplitudes at different locations. So it can excite something, which would be white areas, and it can inhibit something, which would be a black area. So what would, for example, this filter here learn? Well, it emphasizes something that goes like this, and it de-emphasizes something that is in parallel next to that. So that would actually try to identify, or it identifies edges, right? Edges that have a certain orientation, okay? This one here, for example, it would learn some checker kind of like texture that might not actually happen in natural images. So you have to compare natural images like with animals versus like handmade or manufactured images. Then you have color patches, so you can learn different color differences in the images. So these filters are learned themselves, but the traditional approach would have been to just like give the network some filters already, like hand designed. The interesting part is that these Gabor filters are the ones that people actually hand designed and used for a long time in image classification or image recognition or face recognition, like the Viola-Jones algorithm operates on these kind of Gabor filter-like features. So this is something that is very interesting to see that like these neural networks learn something that humans had in mind before, and you can use these filters in many different applications. So what people also are doing is they take pre-trained convolutional neural networks and then just retrain the output layers to do some classification in the end. Okay, so that's one application. Is there questions about this? This is just giving you a kind of like a flavor of what we're going to talk about more towards the end. These are more advanced methods. But I feel like people have heard about this quite a bit recently. Okay, other methods like recurrent neural networks, they don't just take the input or like one single image into account, but they actually can take into account sequences of images, for example, or sequences of words, and they can be used to, for example, investigate different sections of the image in sequence and try to come up with captions. So, for example, the caption for this image that was generated by one of these networks is "Man in black shirt is playing guitar." It's pretty good, even though he's not playing guitar, right? You can see that he's tuning the guitar. So it kind of learns something related to what's going on, even though it's not completely accurate. Or a boy is doing a backflip on a wakeboard. Well, there is water, it's doing something like a backflip, but there's no wakeboard, right? So it learns something about this image, but it's not completely understanding, but it's very, very impressive what's going on. So, but this, for example, is perfect. I mean, like nobody would describe that in a different way, right? So these neural networks are different in the sense that the previous one that we had here, you get one input, you produce an output, and you forget everything about what happened before, right? So there's no state that you like push through over time, so you don't hold information about what happened before. But these recurrent neural networks are networks that have a state that gets fed in sequence. So you understand, like what these networks are doing is they use external input that comes in sequence. So you get like one image after each other, but you're also keeping information about the previous state in mind. So this is how you can analyze videos. This is how you can analyze or generate captions for pictures. This is how you can do speech recognition. Okay, so just again as a flavor. And then very recently, another kind of method has sprung up, so to say. I think that mostly 2016 when this happened are these generative adversarial networks. And these are very interesting because they kind of form a unsupervised, or they transform an unsupervised machine learning task where you have tons and tons and tons of data, but you have zero labels. You don't have any labels for them, for these data points. And they transform an unsupervised learning task where you have a lot of data but no labels into a supervised learning task. And they do it the following way, that you have your images or samples or whatever you have here. So these are a large number of data points, and they get fed into a discriminator. And the discriminator could be, for example, a convolutional neural network, could be an LSTM or something else, or like a recurrent neural network. And the discriminator has to decide if the image that it just received or the sample that it just received was a real sample or generated by this guy. Okay, so it has to make a supervised decision, real or fake, even though these labels have no, or these data points have no labels. But they have a label in the sense that they were collected by you or they were generated by this guy. And so these two networks they will look very similar even though they do completely different functions. So this guy just generates fake images or fake samples, and this guy has to decide, are these fake or real samples? And the interesting part is that with these generators, it can now generate these very intriguing pictures. So this is a network that is trained to generate bedrooms, pictures of bedrooms. And I think it's very, very cool what it does. I think if you're sitting further back, you'll be like, I don't see a difference between, like, I can imagine that this is real, but if you're very close, you can see some weird artifacts sometimes happening in these pictures.
Where can I find this dataset?
I think I should probably put links here, but I can find it again, but it's like generate bedroom pictures,
okay.
but there are even more impressive ones right now. I think some of some recent papers that were published at NIPS in December generate like pictures of animals like birds, and they just look very, very, very interesting. So this is kind of, and people have come up with ideas to generate art, like you can generate art that looks like Monet, or and so it's very, very interesting stuff. Okay, so but this is where we want to go to. This is what we want to understand in this course. But these are very advanced methods, and I think we're like hopefully get there in a good pace. But I think what we need to do also is to understand the basics and to understand like what the ground rules are in machine learning. And so that's why I just wanted to give you like an outlook of what is possible.
So quick question here. So this this diagram actually enables us to, when we input some sample images inside of it, you'll be able to identify whether it belongs to this category or not.
Mm-hmm. So what these networks are doing, they're not designed to, well, they are still really good at discriminating between real and fake images, but the idea of this network is in the end to generate something that looks interesting or looks real. Okay, so it's not like they're not serving a purpose of really like classifying real versus fake images.
So this is like a training process.
This is the training process, and this is kind of like the result.
Oh,
But being able to generate something interesting. And maybe I can show you one of the examples where we used this, where we used the representations that are learned by the generator and discriminator to classify emotion better in speech. So we have used it in like a further task, but usually these networks are not like used for their classification performance, but for their generative and their representation performance. Yeah, you had a question?
Well, there was a generative model, OpenAI research that they just started. I guess there's like only one link to it.
Yeah, they have one of their ongoing research topics is generative models. As I said, it's very, very much on vogue right now.
Okay,
2016, 2017, I think.
Yeah, it was only like one link, but there's more.
Yeah.
There's more scholar articles in regards to that as well.
Yeah. There's so much work happening on this. Okay, good. But before we get to those, I would like to introduce some of the work that we've been doing, and I think Li-Xing was also involved in some of this. So we, as I mentioned, are interested in trying to understand like how individuals behave when they have certain psychological disorders, and the one that we were mostly, or the two that we were mostly interested in were depression and post-traumatic stress disorder. And just as a brief motivation, depression is very prevalent throughout the population. Also, PTSD is quite frequent, not only in service members, but also in civilians. And another thing that we observed is that there's a high comorbidity between depression and PTSD. So if like one or the other is happening, a lot of times the two are overlapping in a sense. And I would like to show you an example of how one of our experiments or virtual humans looks like when we try to understand if individuals suffer from depression. And so this is kind of like an interaction between this individual talking to a virtual human that's displayed on the screen. And what you see overlaid here are the features that we use for the assessment of depression. So in contrast to like the convolutional neural networks or the generative adversarial networks, we are feeding actual features instead of just pictures into the machine learning algorithm. So we extract features that we think are indicative of depression. So let's have a look at this video.
Hi, I'm Ellie. Thanks for coming in today. I was created to talk to people in a safe and secure environment. I'm not a therapist, but I'm here to learn about people and would love to learn about you. I'll ask a few questions to get us started. And please feel free to tell me anything. Your answers are totally confidential. Are you okay with this?
Yes.
So, how are you doing today?
I'm doing well.
That's good. Where are you from originally?
I'm from Los Angeles.
Oh, I'm from LA myself. When was the last time you felt really happy?
When was the last time? I don't know. Yeah, I'm not someone who's really like, I don't have any real highs. I feel like I'm a level person. It's just happy. I guess to answer your question, probably a couple months ago.
I noticed you were hesitant on that one. Would you say you are generally a happy person?
I'm generally happy.
So this kind of gives you an idea of like what this interaction looks like. So we have the virtual human asking certain type of questions. It can ask follow-up questions, and we try to collect as much revealing information as possible within these interactions. And so what really is going on in the background is we try to capture the behavior and try to understand if this behavior is related to depression or PTSD. So for example, and we're going to go into detail what voice quality means, but so for example, we extract that this individual has a voice quality parameter around 0.2 or something like that. That doesn't really give us a lot of information yet. But if we collect this over time, so we can see that there is something like a trend going on, so the individual is changing their voice quality over time. But still, we really don't know if this is related to depression or if it's not. So we kind of like need to fill in this blank box here. That's called reference population. So what we did is we collected a larger number of these interactions, and I think we are past 650 already, so we tried to make this a big data problem. We are collecting more and more data in this regard, and we try to fill this box here. So now we can fill this and say, well, distress sounds like this and not distressed sounds like that. And so we see that this individual is kind of like moving from the non-distressed category towards the distressed category. Okay, so this is kind of like an indication this person might have depression. Okay, but there's always a little bit of caution necessary here, and like it's not like a single individual behavior doesn't relate to depression or a certain category. Nor does it, like in all machine learning experiments, if you see like a certain feature present, there's always a likelihood that this feature does not necessarily always discriminate perfectly. So you need to think about this more of like a multidimensional problem. So that's also what we did we kind of see this as more of like a blood sample test where you come into the lab is kind of like this camera and this microphone, and you behave in front of those, and then we get assessments of your smiles, your voice, your posture, and your overall emotional expressivity. And the collection of all these observations and behaviors kind of serve two purposes. On the one hand, they support clinicians with their assessment so that we can give this to clinicians and say, hey, this guy had a decent smile level, but their emotional expressivity was over the top, right? That was too much or something like that. And so we can provide clinicians with this objective additional information. But also what we use these informations for, or these data points for, is we take them and we put them into our machine learning algorithms. And I'll walk you through one later, but what we try to do is we try to find ways of combinations of these behaviors and how they relate to depression, okay? And since we are not experts in this and we collect a lot of data, we feel like the machine learning algorithm should be able to identify the combinations and the relationships itself. So this is kind of like where we move from explainable data points towards more of a black box, and this is kind of like what machine learning often does. And the more dimensions you have, the more complex your data set is, the more black box your machine learning algorithm becomes. So in the work that I'm doing, where we are interested in human behavior, we also always have to kind of serve two purposes. On the one hand, we try to understand what is happening and try to give actionable information to clinicians, to instructors, to officers and trainers. And on the other hand, we want to have the most performant machine learning algorithms and models that might not be that explainable, but they produce a really accurate assessment. So this is kind of always a little bit of a balance in our work. Very important, this is not to replace healthcare providers, but to support them. But it's just kind of like a disclaimer. Application areas, just for visualization, well, we think that we can reach a lot more people with these virtual humans because they cost no money after they have been developed, and we can deploy them online. And the second purpose is to help clinicians better understand what's going on with individuals' behavior. And I would like to walk you through one of these experiments, and I'd like to show you how this kind of research came about, and basically also how we identified what is present in the nonverbal behavior of individuals that suffer from depression as kind of an analogy to that just because we have powerful machine learning algorithms doesn't mean that we should not know what's in our data. Okay, so if you collect the data set, it is always very well worth your time to investigate, to take a look at the data and try to understand what's present in it, and to also understand what the other people or other experts think about this data. So what we did in our depression analysis data set is we went into the literature, and you see these are papers from quite a few years ago, even in 1974, and we looked at the literature and found that individuals have identified a lot of nonverbal behaviors that are related to depression. So for example, what do we have here? Reduced gestures, reduced speech, long pauses, increased gaze aversion, reduced emotional expressivity. So we found these behaviors online and in those papers, but now we need to kind of try to find ways to extract those features and to understand how they are present in our data. So this is kind of the process that we went through, understanding what's happening. So, but why did we do anything, or why did we continue to work on this if people have already solved this? Well, they solved it in a certain way. They did it manually. 1974, they didn't have convolutional neural networks or very high performant deep learning. And they don't have quantitative assessments. They observed it subjectively. Like they interviewed psychologists and psychiatrists. Like, what did you observe when you interacted with individuals that suffer from depression? Well, I think they weren't as emotionally expressive. But like, you don't have a number for that. So what we wanted to do is we wanted to try to understand quantitatively what's going on. And so here are a couple examples of lower gestures in speech, lower pitch, variabilities of pitch is kind of like the fundamental frequency of my voice. So this is a low pitch, this is a high pitch. And so speech monotonicity is increased, so that means like the speech is kind of flat. And then they also identified that there is vocal tension present. Okay, and so I'd like to walk you through one of these examples, and the vocal tension is one of them. And so the voice quality of an individual is kind of like reflecting the timbre or the coloring of the voice. So there's an inherent aspect, so my voice sounds differently in voice quality than, for example, a female's voice or a baby's voice. But there's also a communicative aspect to it, so I can modify my voice quality dynamically and superimpose this onto my inherent voice quality to serve some communicative purposes. And these communicative purposes, for example, are paralinguistic signals such as like mood or affective state, so I can change my emotion by changing my voice tenseness. So this sounds very modal, but then when I get angry, like my tension goes up, okay? So the voice quality changes if I have a different affective state. There are social factors like social standing and interpersonal relationships that affect the voice quality. So if you have communication with an intimate partner, your voice quality becomes more breathy and more soft in a sense. And if you're talking to your boss, you might also have the more soft voice, So these social relationships change your voice quality as well. And other languages like Finnish, for example, use voice quality changes even for like turn management to communicate better with other people. So a couple of examples here. These are a little bit laughable examples, but they give you a good idea of what's going on. And the voice quality is mostly influenced by your vocal folds and their vibrations. So the vocal folds sit around here, and they vibrate while you produce voice. And the signal in the end is like just a vocal fold, like voice, for example, sounds like ah. So that's like very, very flat. So there's no modulation. It changes there with respect to what you're saying. So the vocal folds are not responsible for changing the the vowels or the syllables that you're saying, but they're more reflective of the pitch or the fundamental frequencies. So the glottal pulses look like this, which basically just means that the vocal folds are opening, air is flowing through. When they're open, air is flowing, like most air is flowing through, and then they're closing, and they're shut again, and because they're not perfect machines, they shut like this, and they go into a relaxation state, which is basically reflected here, and this discontinuity there. But this is just an example, so don't worry too much about this. But if you have different types of voice qualities, these shapes change, and this is what we want to get at. That's what we want to represent, and what we want to provide the machine learning algorithm to learn that there is a change in voice quality. And this is how they sound like.
Where were you while we were away?
This is breathy or lex voices.
Learning to speak well is an important and fruitful task.
And then you have modal voices, which is basically the normal
Where
voice.
were you while we were away?
Learning to speak well is an important and fruitful task.
Then you have tense voices that sound a bit funny.
Where were you while we were away?
Learning to speak well is an important and fruitful task.
And so what we try to do here is we try to understand what these parameters are that create these shapes. And so we are interested in these kind of relationships between certain amplitudes on these graphs, and they're really, really difficult to extract, but these are what reflect voice quality differences in our data. So we need to come up with ways to investigate those, and we need to find those instances. And in the past, people have gone through a lot of effort to identify this. So they have used, for example, the electroglottographic evaluations, where they use like sensors here at the throat to like identify these pulses and to measure how the voice quality changes. But what we wanted to do, we wanted to bring machine learning into this process, because this is very complicated. It takes a lot of time to do this. So we wanted to try to see, and this is kind of like an example where I would like to show you that machine learning is not just useful for classification and for evaluation or whatever of your data, but it's also useful to generate new data and to do feature extraction itself. So what we did here is we trained a neural network to speed up this process, and we used the ground truth of these electroglottographs as our training data. And so we tried to find this open phase automatically. And what we did is we compared our method to the other standard methods and tested it on a completely new data set that we have never seen in the neural network. And so this is kind of like how we trained our methods. We took raw audio, we extracted mel-frequency capsule coefficients. Doesn't really matter what they are, but they're kind of like compact representations of the spectrum of what's going on. We put that into our neural networks and tried to estimate these clotting flow parameters. And it's interesting that our method outperformed all other methods on the data that we have seen, and even the unseen data. So our method is closest to what the ground truth is, and the other methods have quite significant problems with this task. And in the end, we even show that in a speaker-independent evaluation, we are still outperforming all the other methods. But what is most important, I think, is the fact that we can run this in real time, and we only require 0.4% of real time to run this, because neural networks, or most of the other machine learning algorithms, have this characteristic that once you have trained them, you have done most of the work. And that's why they're also very useful for speech recognition, for example. Like, I don't have to train Siri, or I don't have to wait very long for Siri to answer my question. It just pushes the audio through the network, and you get the output, this can be very computationally very fast. Once you trained your network, you don't have to do a lot of work anymore. While the other methods are based off of like standard optimization algorithms, take 15% of time. So this is kind of like if you have a second, you need 1/10 of a second to calculate it, and other methods even have 200%. So if you have a second of audio, you need 2 seconds of audio, 2 seconds to calculate it. So these methods are a lot slower and than our method, and even outperform. So this is kind of giving you a motivation of like why machine learning can be quite important, not just for classification, but also for processing audio and feature extraction. All right, let's take a 10-minute break and then continue on some more experiments.